will repeat what I just said. I didn't pay attention to it. So the comparison between both of the two sides, it's easy to notice. It depends on the application for which this hollow fiber, as I said, membrane used. We can see in case of the removal of bigaments or dyes from textile industry or coloration or something, if we have any large molecular weight molecules, it's easy to use from inside to outside flow, because in such a case the layer formed will be very tiny and thin, and in such a case we can easily remove it by backwash. But in case of large particulate or clay particles on the membrane itself, or on used in the raw water itself, it will start to precipitate, accumulate, forming cake layer. So it is better to use this technique where I have a space and the ability to remove the particulate or the cake formed on the membrane surface. So in such a case, I recommend it to use from outside to inside flow. So I hope, as I said, the application can clear for you which technique you can use from inside to outside or outside to inside. Which one is suitable for you? It's based on the application for which you are using this technique. So it is clear? Okay, you are welcome. So this, as I said, for the pressurized hollow fiber membrane. So as we see in this figure, the fibers located inside, from one side has, as I said, this reason, and can be also one seal around just to make it watertight from both sides, and the fiber itself freely located inside the pressure vessel. Of course, the dimension of this unit or the fibers, including diameter, including the length of the hollow fiber itself, depend on the membrane type itself. So you can find it, for example, less than 1 meter up to 6 meter modules, and the diameter also you can find it just tiny, around 4 inches or less, to up to 250, 300 milli diameter, which is used for wastewater treatment and produced by some producers or some companies. So this is, as I say, for hollow fiber modules inside pressure vessel. Let's see the other type, which is, as I said, submerged, which is submerged. So we discussed in this, we show in this figure, as I said, the hollow fiber, which can be mounted, as I say, as pressurized system. It's only pressurized under pressure to be inside, as I said, this housing, as I said, which is different in shape, different in diameter, different in position. You can find it vertical, you can find it horizontal. Mounting, it is largely different, as we will see in some videos next lecture. So the other type, which is, let's move to it, which is the pressurized ceramic modules. The pressurized ceramic modules, it can be the same, either to be mounted inside the housing, or can be inside other type of housing, as we see. This is enclosure, we can say enclosure. This is standard housing. Two types, as they say, of membranes can be found. This dead end filtration type, which we can see it is very tiny holes in front of us, and in such a case we can find that this is the feed in gray and the blue is the filtrate. So we have from the feed side go into inside, close the channel from the end, and the other channel in the opposite direction open for the filtrate. So this is mounted with gasket inside, as I said, the housing, or inside the enclosure, as we see it. This is stainless steel enclosure firmly closed. We can see it very watertight. So this is, as I say, this type of bulk modules dead end filtration, but it can be also inside housing, and it can be, let's see the figure and then explained on it. So this is, as I say, inside the housing, as I shown before. We can see one closed, one open, one closed, one open, very tiny. And this is, of course, the flanged part gasket for the feet side, or, as they say, the filtrate side. It can be either from outside to inside or from inside to outside. If we consider this type or this model, it can work, for example, for sucking and pressurizing. This can work as pressurized system and sucking. So it's dual application. Okay, it can be used as pressurized and it can be used for sucking application. Let's see to this type also of inside vessel ceramic membranes. It's shown in the figure. As we see, we have it in different shape. The first is it's just, as I said, group of plates. If we check it, we will find some closed, some open, exactly as in the other type, but just different in shape. And instead of having it as a one block, and we can find this flanged side from it, this is almost close or similar to the hollow fiber type. I bought both of them next to each other just to compare how it looks like. It's the same, almost the same, but just as I say, it is ceramic instead of hollow fiber. You can see the reason, just molded outside it to make it watertight or firmly closed from both sides, as I say. Okay, so this can work, as I say, for sucking. So for the ceramic membranes, it can be applied for dual application, sucking and pressurized inside the pressure vessel itself. But for the hollow fiber, it is just pressurized system. So the hollow fiber membrane and the tubular membrane. Ceramic tubular membrane can be of dual application, can be used with suction, can be used pressurized. But for the hollow fiber membrane, it is always pressurized. It is always pressurized. We have another shape which is similar to a cartridge filter housing. We have this for cross flow or dead end filtration. Mostly it is used as cross flow filtration. It's we can see it. By the way, this also can exist in our daily use. Nobody can pay attention to it. It is the catalyzers in the car. It is used for air, for the exhaust of the car. It is similar to it exactly. It's similar to it exactly. It's a ceramic membrane and can be dead end filtration. For this, when it started to be fouled or closed, we started to lose the efficiency of separation, and at the same time it's afford the back pressure to the engine and can give higher performance for as I said, the fuel. So let's come to our main point. As I say, this is the tubular, this is the hollow fiber type of membrane. Let's see the flat sheet application. Sorry, submerged application. The submerged application, let's consider the polymeric membrane. We have two types as shown in the first figure and the first classification page. We have the flat sheet and we have the hollow fiber. We have the flat sheet and we have the hollow fiber as shown in the figure. We can see it clearly in this figure. So we have, as I say, if we checked it, how it is made or manufactured, we have a frame. This frame with, let's say, water transport material inside of it can be just, as I said, wave-on or any supportive layer. Any supportive layer work or act as a channel way for the filtered water. Work as channel way for the filtered water. We have this frame and we have this, as I said, transporting or, as I said, supporting material inside the frame. We can notice here one tiny nozzle or small nozzle. It is used for sucking. It is used for sucking. So all submerged application, we locate the module or the membrane inside a tank, and of course it is sucking application. For the flat sheet, as we see it in the figure, we have the frame, we have the water transport or the supportive layer itself, and the nozzle for sucking, and we have two sides. From both of the two sides of the this frame, we have the membrane layer. The surface area is just both side surface area in such a case, because we have left side and right side, left hand or right hand membrane layer. So the sum of both of them give us the membrane surface area. This membrane, as I said, flat sheet membrane element, ultrafiltration flat sheet membranes, arranged in one cassette. We call this construction cassette, and it is connected, the suction side connected to the main header or the main pipe by a set of flexible hoses, transparent flexible hoses, as we see it connecting the nozzle of the membrane and the main header. The sucking, of course, should be suction side from this main header across the hoses and from inside the membrane across to the membrane surface from both sides. This cassette, which we call, can be made from galvanized steel, can be made from stainless steel, different grade 304 or 316L. It is different grades depending on the alloying elements in the stainless steel itself. We can find that it is the cassette consisting of two compartments. The upper one, which has the modules itself or the membrane sheets next to each other mounted, and the lower compartment, which has a set of coarse bubble air diffusers. The function of these coarse bubble air diffusers is to generate or to have fine bubbles of air, just removing or assist to remove this cake layer accumulating on the membrane surface. So in case of, if we are applying this for wastewater treatment, for example, the distance between these sheets, the gap between these sheets is controlled, of course, according to the application. If I am using it for wastewater treatment, it is a little bit wider space between the membrane sheets itself. If it is used for chemical separation or for pharmaceutical industries or any other application, it can be, as I said, smaller gap or distance between the two successive plates. For the bottom part, as I say, we have this air diffusers, coarse bubble, to generate air bubbles. These air bubbles move across the space between the two sheets and started to remove or make movement, turbulence between the two plates to remove this cake layer accumulated on the membrane surface itself. So this is, as I said, the flat sheet. We have in general this main header for sucking the water or the fluid, and here for air. And this is, as I said, the cassette, which consists of several membranes arranged successive next to each other. The gap depends on the application for which we use this kind of elements. We'll see from the other side the hollow fibers. We saw already how it is binded together in the pressure vessel to form this pressurized system. We have it here in different way. We have like a frame, we can say upper rectangular part and lower rectangular part. The fibers connected between both sides, upper and lower. It also has like a reason around just to make it sealed properly, and from both sides. And the upper part, we can see here, the upper part from left side and right side, it has a place for connections, like to fix a connector from both sides, left side and right side. So we have in general, this is the membrane modules. It's a set of hollow fiber, just like a sheet arranged in one level. It has from the upper part, as I said, one connected to the suction side. From the lower part, it is blind as we see it here. It's just, as I said, one part to gather all fibers. So the fibers just opened from the upper side, and the suction process coming from left and right side with a special connector, which we can see here, connecting the hollow fiber module with the main sucking header. We have it here, double header, not like the flat sheet, just one, as I said, nozzle in the middle. No, we have it here, connection from both sides, left and right, each one connected to one sucking header, as we see it in the figure. Okay. The same thing, we can see it as we saw it before in the flat sheet. This is the cassette. This is what we call cassette. So we have in both the flat sheet, we have the membrane elements, we can say the flat sheet membrane arranged in one cassette, and here we have what we call module, the set of hollow fibers, as I said, connecting to one rectangular part or flat part, upper and lower. This what we call module. It is sealed from downside and open from both sides, left and right, in the upper part for suction. In the same way, we have the lower part for, as I said, diffused air. It has coarse bubbles, air diffusers, just to make, as I said, much or many air bubbles, liberating the thick layer from the surface of the hollow fiber itself. Some of this hollow fiber, we can see it mounted not in vertical position like that, but some products or some companies fix this type of modules or cassette in horizontal shape or horizontal assembly. So they say from their point of view, it is more convenient for the release or the removal of cake from the membrane surface, as from here it's tangential to the fiber itself, so it is not efficient. But in the, if we fixed it in horizontal position, it will be more efficient, as the fibers will start to to be, as I said, vibrating too much with the air bubbles liberating all the cake around. So the backwash time will be longer in such a case. So as I said, the design basics depends on, as I said, different from one company or one manufacturer to another. The third thing, which is, as I say, the ceramic membranes. The ceramic membranes we can find in general in two types. The first type, regardless, of course, the material used for it, if it is titanium oxide, zircon oxide, alpha aluminum oxide, silicon carbide, it depends on the material. The material, as I said, different, but the main assembly, we can see it is almost the same, almost the same. Either we can see, let's see the manufacturing process for it here, as shown in the figure. The membrane extruded by this machine, extruder. We have the powder of aluminum oxide or silicon carbide, and it's extruder through certain, as I said, extruding machine to make it in the shape of flat sheet with tubes inside or just channels inside to collect the permeate or the filtrate. And then automatic cutting reel, it's just a line of nylon, you can say, just pass quickly to cut these sheets. You can say it's like a knife, pass across the sheet formed or produced to cut it, as I said, in sharp way, very flat without affecting the holes inside of the membrane itself or the channels inside of the membrane. So the produced flat sheet just move slowly on the production conveyor and then to like one flat part sheet, this flat sheet to, as I said, preserve it in the same form without any deformation in its shape. After that, it passes through a dryer to dry it. The particle size of the ceramic material used for this, it's around, let's say, 10 to 50 micron, 10 to 50 micron. So we have it from coarse material. So this is the basic frame for the ceramic membrane. You can say it is formed from coarse material in the beginning. This coarse material ranges in size between 10 to 50 micron size particles. After that, it passes through these furnaces. These furnaces differ largely according to the type of membrane which we are producing. You can see this very long assembly. It's very long, as I said, production line, a very long furnace with heaters, can be, as I said, operated by gas or can be operated by electric, as they say, to have such a shape in front of us. So, as I said, this is for alpha aluminum oxide. This kind of furnace is used for alpha aluminum oxide. We should consider the material and the temperature range used to manufacturing it, and also the atmosphere around the type of membrane produced. Let's see what happened. We have this, as I said, the coarse material layer, the basic layer of the ceramic, as I said, material, which I said from 10 to 50 micron. This is the coarse side. This 1 micron is the fine part here. So these coarse particles, as I said, started to go inside the furnace, not to have complete fusion, but just we can say or define as incipient melting. What is incipient melting? Incipient melting is the fusion of the particle edges to stuck to each other like that. Just to be, you can see here the cut part, it is just, as I say, stuck to each other to preserve the porosity of the formed structure. So we have, as I show, this these plates consisting of, as I said, large particles from 10 to 50 micron. And as I said, it goes through the furnace to have incipient melting. Incipient melting at very high temperature depends of the material of the membrane. The melting happen or take place for the edges of the particles. We have here sharp particles started to melt together. You can see the effect of heat just started to be rounded a little bit, stuck to each other, one particle fused to each other to maintain the structure and in the same time to keep the porosity. In general, we can say for alpha aluminum oxide, the incipient melting can take place around 1200 degree till 1350 degree. 1200 degree, 1350 degree. This is, as I said, for silicate. Sorry, for the alpha aluminum oxide. The alpha aluminum oxide furnace, normally has a refractories inside of it to seal it, to protect from the temperature from zirconia. Zirconia can take up to 1650 degrees Celsius, so it can tolerate, as I said, the temperature of the incipient melting or fusion of the edges of the ceramic grains. Okay? If we checked, as I said, the alpha aluminum oxide, we said the refractory material in the furnace itself, it is from zirconia. What about zirconia? Zirconia has another category of insulation material inside the furnace and the higher temperature range, because we already understood that the temperature for melting for the zirconia refractories is 1650 degrees. The highest all over ceramic types is the most complicated production process we can find in the silicon carbide production. The silicon carbide production process should be, from one hand, not in very long furnace as shown in the figure here. No, it is just a compartment, closed furnace. This closed furnace has inside graphite refractories, because it can tolerate up to 2000 degrees Celsius. The melting point for the incipient melting for silicon carbide is around 1800 degrees Celsius. 1800 degrees Celsius. I'm reading your question and I will answer it when I finish this point to highlight it, not to come back to it again. Okay, so for the manufacturing process of silicon carbide ceramic membranes, it takes place in closed furnace filled with argon gas. Argon gas, this means it is vacuumed, filled with argon gas to avoid the as I said, the effect of the complexation of nitrogen with the silicon and the carbon, the nitriding process. Okay, and in such a case, it will damage the membrane or will have very bad quality membrane produced. So we manufacture the silicon carbide membrane inside closed furnace, vacuumed, filled with argon at a very high temperature, 1850 degree, and the refractories inside of it, it is around 10 to 20 centimeter. I saw it in some furnaces already from graphite. From graphite, it can take temperature over 2000 degrees. So this is simply, as I say, the production process. Now we have, let's see your questions. How does particle size affect the efficiency of flat sheet submerged ultrafiltration module? I cannot understand your question. Can you please clear it in different way? And what is the maximum particle size that can be removed by this system? I already explained it's over 5 nanometer. I already explained it's over 5 to 10 nanometer. Okay? So this is for your question. What is the effect of temperature on the formation of this type filter? We are not talking about filter. We are talking about, as I said, membranes in such a case. And the temperature, we cannot say the effect of temperature. We can say the required temperature for the manufacturing process. The required temperature for the manufacturing process. For ceramic membrane, everyone has temperature, melting point. This melting point should not be reached to make complete fusion. And in such a case, it will be like a glass, impermeable. No, it should be just sufficient for the incipient melting. What is the incipient melting? Just the melting of the borders of the particles to be stuck or glued together, fused together to maintain or keep the permeability or the pores inside this structure. Okay? Can you share the recording, please? Which recording? Can you please clear for me? Where is the option of closed caption in Zoom? I cannot also understand your question, Walid. Can you please explain, Walid, what is your question? Where is the option of closed captions in Zoom? So anyhow, I hope I answered already your question. Yes, I'm with you. I'm listening. Somebody has a question?
No, sir. Sir, please skip that question. He was asking about some technical issue.
Why is there one channel open and one closed in ceramic membranes? Who said so? Who said so? You can see in this flat sheet, both ends open. Both ends open. It depends on the form or the shape of the membrane. It can be tubular. In such a case, it will have one closed, one open. In such a case, to be used for dead end filtration. But here in the flat sheet, you can see it is the channels is open from both because the filtration from outside to inside in such a case. But from the other one, it alternate one channel for feed, one channel for permeate, as in the I will come back to the figure to show it to you. Does the pores diameter affect the efficiency of the flat sheet filtration? I didn't complete yet. I will inform you about this question. I didn't complete the manufacturing technique. Why there is one channel open? Okay, I answered this question. So let's come back to our, as I said, topic, which is the flat sheet. Now I have, as I say, flat sheet membrane formed like that already, as I said, enter the oven in production or the furnace in production and produced, as I said, very consistent, very strong flat sheet membrane. I would like to highlight one very important thing, that the brittleness of this plate differ between one type to another. The most consistent and very strong one, durable, is aluminum oxide. Really, you can transport it without much precautions required safely, no problem at all. It will not be damaged. And the opposite of that, silicon carbide is very brittle. And too much precautions should be considered during the transportation of these modules and the plates. So this is, we should consider, as I said, in handling of both type of membrane, flat sheet ceramic membranes. This is the question which you asked, as I said, it's apply, as I said, for dead end filtration. and you have one open, one closed, one for feed, one for filtrate. As you see, it is different. This is for dual application, sucking, and in the same time pressurizing, but the other one, the flat sheet, for just sucking. Let's come, as I said, to the main point that we have now formed the basic layer or the basic structure of the membrane with a very large size, let's say, as I said, 10 to 50 micron particles. And what is the next step? The next step is the formation of very fine layer consisting of 1 micron particles or less than that on the surface of this layer. In case of silicon carbide, we can form this layer easily just by making like a mud solution. This mud solution is from silicon carbide, very tiny particles, as you see, 1 micron. This almost liquid or very muddy solution, you can say, slimy solution. We take the plate and just put it inside the solution and take it out. So this process causes this, as I said, the membrane is very hygroscopic, and in the same time, as I said, has will suck immediately this solution and leave the particles, forming a surface layer on this coarse layer of silicon carbide in such a case. So this is how it's made for the silicon carbide membranes. We have, as I said, this coarse particles layer, the main frame, which we call the flat sheet. We just submerge it inside the mud solution or the silicon carbide fine particle solution made. Then we take it out, so one film layer will be formed on the surface. This film layer, as I said, kept to dry, and after that go to furnace to be melted again, or as I said, as the first, as I said, main frame formed. It's the same, as I said, technique, just to make, as I said, incipient melting for the edges. In such a case, because of the particle size is very tiny and small, the fusion, as I said, of it, or the edge fusions will be will not require or necessitate very high temperature. So we are doing it at lower temperature limit. So this is for silicon carbide. What about alpha aluminum oxide, zirconia, and others? For alpha aluminum oxide, it's
So
a little
this session is about.
Sorry?